Hello, in these videos we're going to be going over the basics on how to use GaussView for your computational chemistry experiment. These videos will serve as an accompaniment to your lab handout, as it's often hard to connect the dots on what computational instructions are asking you to do, especially when they're for software that you've never even used before. So before we talk about GaussView, we need to talk about its sister program, Gaussian. And Gaussian is what we call a computational suite. So, introduction to that. So imagine you want to simulate a ball rolling down into a valley until it stops, reaching its lowest energy point. What do you need to know to do this simulation? Well, 4 things. First, you're going to need sufficient description of what the valley is shaped like. Second, you need to know where the ball starts, its mass, and the shape of the ball. Then also, a sufficient description of the forces at play. So here, we know that gravity is uniform, and that the hill will have an equal and opposing normal force. So if we were to run a simulation of what would occur with this ball, we would see that first, the ball would start rolling, normal force would push it this way, the gravity will push it down, and it'll be falling until it lands here, and it comes to a rest. This is what is known as an optimization. The ball is now optimized to its lowest energy at the bottom of the valley. You might also be familiar with what is known as like an energy diagram. So we can represent the energy of this system to help us understand what's going on over these steps. So at the beginning, it has all this energy, the ball's way up here, the ball's falling, it's expending that energy until it's at rest. It's at a lower point, there's less energy, but most importantly, it's stable. Now what Gaussian does is not unlike simulating a ball rolling down a hill. It will take in information you give it about a molecule and roll it down a theoretical hill containing approximations for the quantum mechanical forces at play. So say you knew that water is an oxygen with 2 hydrogens, but you didn't really know much beyond that. So you take a guess and say it's this linear looking thing. What Gaussian does is not unlike simulating a ball rolling down a hill. It will take in information about a molecule and roll it down instead a theoretical hill containing approximations of the quantum mechanical forces at play that thankfully you don't have to understand to do this experiment, and you can still get a lot out of it. So let's say you wanted to figure out the structure, all the angles and bond distances and whatnot of water, but you don't really know much about water to begin with. So you give water looking like this, just a linear molecule, perfectly flat with hydrogen on both ends. Well, when you account all the quantum mechanical forces that would result from a structure like this, it's not good. It's kind of like the ball at the top of the hill. It's ready to roll. So what Gaussian will do is it will simulate that and optimize its structure a little bit at a time until it becomes at rest in the actual natural configuration of water.